Okay, so let's proceed with our next topic here on topic 9, arithmetic logic. So these are the topics we're going to cover. We're going to look at the half adder, the full adder, combining the full adders to obtain the ripple carry adder, followed by the subtractor, comparators, parity generators as well, and finally we're going to look at the basic shifters. So let's look at the half adder. So what is a half adder? So a half adder is basically is adding 2 bits of numbers. So we have 2 bits here. Okay, so we have a 2-bit number, 2-bit binary, A and B, and we are going to plus them together. So if we plus 0 and 0, we are going to get the sum, which is S, equals to 0, and the carry will be 0. 0 plus 1 will be equals to 1, where the sum is 1 and the carry is 0. 1 plus 0 is 1, the sum is 1, the carry is 0, and finally 1 plus 1 equals to 3, and 3 is 1 plus 1 equals to 2, and 2 in binary is 1 0. So we have the sum is actually 1 plus 1 is actually a sum of 0 and a carry of 1. Okay, so we have the truth table here. We have the truth table of the half adder, and from there we can obtain the Boolean equation. So how to obtain the Boolean equation? You can simply see from here that our carry is equals to 1 only if A equals to 1 and B equals to 1. Therefore our carry here, we can see that C is equals to A dot B. And our sum, we can see here, is in fact a XOR operation is equals to 1 when either of the A or B is equals to 1. Therefore, we have a XOR operation here for the output S. So if we extend our half adder, we can get the full adder, where the full adder is now adding 3 bits. So that's the main difference between the half adder and the full adder, where the half adder is adding 2 bits of number, and a full adder, 1-bit full adder, is adding 3 bits of numbers. So the half adder, we can derive the truth table. Okay, we can derive the truth table here, where we can see that 0 plus 0 plus 0 is actually 0. So we have 0. 0 plus 0 plus 1 is 1, 0, 1. And notice the sum is on the right side, the carry is on the left side. So 0 plus 1 plus 0 is 1, and so on. We look at the next one, 0 plus 1 plus 1 equals to 2. Okay, equals to 2. 2 is actually 1, 0 in binary. So if you carry on all the way, and the last one here, we can see that 1 plus 1 plus 1 is actually equals to 3, and 3 in binary is in fact 1, 1. So then that's the reason why we have Ci plus 1 equals to 1 and the Si equals to 1. So here is our block diagram. Okay, here is our block diagram of the full adder, where we have the input Ai, Bi, Ci, and the output Si, Ci plus 1. So Ci plus 1 here corresponds to the carry for the next iteration. So how to implement the Boolean equation? Okay, how to get the Boolean or the gates for the full adder? So we can have a K-map, and obviously we are going to get 2 K-maps. Okay, 2 K-maps. So one K-map to derive the output Ci, and another K-map to derive the output Si. So if you do the K-map carefully and correctly, we are going to get Ci plus 1 is in fact AiBi plus AiCi plus BiCi, and therefore our logic gate level schematic will be simply this. So here is AiBi, and here is AiCi, and here is BiCi, and them together, and we have a plus, and we get our Ci plus 1. And again, if we do a K-map for the Si, we are going to get in fact the following canonical expression. Okay, the canonical expression will be based on 1, 2, 3, and 4 logic 1s on the output SI, and from this canonical we can simplify it to XOR gates. And therefore we have our 2 XOR there, where our S is equal to AI XOR BI, this one, and then the output there we are going to XOR with CI or AI to obtain our final SI. So here is our gate level schematic diagram for the full adder for SI and CI. So these are adding 1 bits. These are adding 1 bit A, B, C. Now, what if we before we look at that, adding more bits of numbers, we look at another implementation of the full adder. So in another implementation, this one is more simplified. Here is more simplified, whereby it's using only 2 XOR, 2 AND, and 1 OR. Okay, a total of 5 logic gates. In the other case, we are using here 2 XOR, 3 AND, and 1 OR. So we can see we have an extra AND gate with a total of 6 gates. Okay, with a total of 6 gates, and here we have a total of 5 gates. So basically here, what happened here is we can actually simplify the full adder to be 2 half adders. Okay, so here is in fact the output here. Okay, S1 is AI plus BI, and the CI here is adding, okay, is adding this one. So here is your CI. Okay, so your final SI. Okay, your final SI. So here we call it S0. Say is AIBI. So your final SI here is in fact S0 plus CI, which is actually in fact is AI plus BI plus CI. Okay, and in fact, how to obtain your carry? Okay, your carry, you can see here that your carry is in fact CI plus 1 is in fact AI BI, which is here AIBI plus with CI AI XOR BI. Okay, so here is in fact AI BI plus AICI XOR AI BI, and this equation actually works for a full adder, whereby is equivalent to our original CI plus 1, where AI BI, AICI, BICI, and here is just another XOR here, and we can actually reuse the answer that we get for the S0 here. Okay, so the two implementations of the full adder, one is a more efficient implementation where we save one logic gate, which is cheaper and also faster as well. So how to add more numbers? So for example, if we have a 4-bit number, you want to add 0101, you want to add with 0110, A plus B, and we know that the answer is going to be 11101, so this is our final answer, and we know that we can actually use a full adder, okay, with a carry. So here is our carry. So if we start with the carry 0, so we can see that we can use a full adder to calculate the first row, the first column of the sum. So the first column of the sum is going to go 0, which is this one, and our A is a 1 and 0. So our A is in fact 0101, so it's a 0101, and our B is 0110, so 0110, and our carry is 0 based on this value. So 0 plus 0 plus 1 is actually 0, 1. So 0, 1. So here actually you can put 0 there. So 0 plus 0 plus 1 is also 0, 1. So we can actually go 0 there. 1 plus 1 plus 0 is actually 1, 0. It's actually 1, 0. So we actually put 1, 0. And finally 1 plus 0 plus 0, which is here. 1 plus 0 plus 0, we are going to get 0 and 1. And here is our solution, which is exactly the same. The answer is 1, 0, 1, 1. With a carry out of 0. So from there, we can extend our adder to convert this into a subtractor. So how to design a subtractor? So step number 1 is if we need to do a minus b, we need to take the 2's complement of b, invert b, and then plus 1. So and then we perform a plus negative b. So for example, if we have a is 0, 1, 0, 1 and b is 0, 1, 1, 0 as in the previous example, and we need to do, instead of a plus b, we want to do a minus b. So what we need to do is we need to convert this to negative. Okay, convert b to negative, which is simply going to be 1, 0, 0, 1 plus 1, 1, 0, 1, 0. So here we have this 1, 0, 1, 0. And then we do a plus. So here essentially what we are doing here is actually a plus negative b. Okay, so essentially it's a minus b. So then we can see that if we do this, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and we see that this particular binary is actually minus 2. So how to prove that? So we can do like this, plus 1. Okay, so therefore here is actually negative 2. Okay, negative 2. So let's analyze this. So how to design the subtractor? So for the subtractor, we need to add 1. Okay, so for example, we had before was 0, 1, 0, 1, 0, 1, 1, 0. Sorry. Okay, 0, 1, 1, 0. So what we want to do is 0. We want to minus okay, this is our original. This is our original equation, but actually what we are doing is actually 0, 1, 0, 1 plus the complement, which is 1, 0, 1, 0. Okay, so we can see here that what we are doing here is in fact 1, 0. So we have an inverter there, 0 and a 1, and then we have plus 1. So we have a plus 1, and therefore we are going to get this particular 1, 0, 1, 0. So we plus 1 on this one. Okay, so if we do this, we are going to get 1, 1. 1 plus 0 is 1. Okay. Okay, so there might be a mistake here. So here is 4 is actually 0, 1, 0, 0. So okay, so we are actually doing this particular operation. Okay, so we want to do a 4 minus 6. Okay, a 4 minus 6. So here is a 4 and minus 6. So here is actually a 4 plus negative 6. Okay, in the 2's complement notation. Okay, so 2's complement notation is 4 minus 6. So here is a 0, 0, 0, 1, 1, 1. And here we can see that 1 plus 1 plus 0. So 1 plus 1 plus 0 is actually 1, 0. 1 plus 0, 0 is 0, 1. 0 plus 0 plus 1 is 0, 1. 0 plus 0 plus 1 is 0, 1. So we see that we get the answer is negative 2. Okay, so basically 2 steps. Okay, just to repeat here, basically 2 steps to convert an adder to a subtractor. The first step is number 1, you need to have step 1 is to have a 1 in the carry. Okay, so because we need to add, we need to do a convert and a complement and add 1. So the second step is to add these inverters to invert the b values. So we basically invert the b values plus 1 on the carry, and then we do a plus the 2's complement of b to obtain the subtracted value, the subtraction value. Okay, and now we move on to the comparators. So a comparator, what it does is a comparator produces an output when the two binary words are equal. They can be used for circuits such as security locks, where binary password is compared to the human input. Magnitude comparators compares for conditions which are more flexible. Let's have a look at the example here for a simplest 1-bit comparator. So a 1-bit comparator we're going to see is AI and BI, are they less than, greater than, or equal? So obviously they are equal, therefore we have a 1 there. It is not less than, it is not greater than, therefore they are 0. 0 and 1, we can see that A is actually less. A is less than B. Therefore L equals to 1. It is not equal. A is not greater than B. In this case, A and B, so A is greater than, okay, A is greater than B, not less, not equal. This one equal, okay, and not less than, not equal. So from here we can get the obviously we can get the Boolean equation slash gate schematic. Okay, we can get both the Boolean and gate schematic using a K-map and so on. So then we can have what the gates inside here is going to look like. Okay, can you generate a truth table for a 2-bit comparator? So for a 2-bit comparator, we have A1, A0. We are going to compare with B1, B0. Okay, and then we have less than, equal, and greater. So for example, if we do a little bit here, 0, 1, 1, 0. Okay, we just do a small example here. Okay. Okay, so and then we can carry on there. So it's a small example how to generate a truth table for a 2-bit comparator. So we see that A and B here, they are equal, 0 and 0. That's what is equal. It's not less than. It's not greater than. In the second case, A is actually less than. This is 0. This is 1. A is less than. So these are not equal. They are not greater. Again, A is less. This is less. Okay, and finally here you can see A is greater than B. 0, 1, so greater, 1, 0, 0, and then we can continue. So once you generate the truth table, we can of course do the K-map, and we can implement the Boolean equation, and also we can implement using multiplexers and decoders as well. So a 4-bit comparator device, so if we need to compare 4-bit numbers, A and B, we can use a 7485 device. Okay, this is available at most electronic shop. You can actually purchase and buy this for a DIY electronics. So we just supply our bit values on the input, and then the output pin here. Okay, so output pin 7, 6, and 5 will tell you if A is greater than, less than, equals, or greater than. And we can also cascade them. So it has a cascade input. So the cascade input is actually used to combine multiple 7485 devices for more than 4 bits. Okay, so these are used to compare equality for more than 4 bits. Okay, for example 5, 6, 7, 8, then we can use two 7485 devices and we just connect the cascading inputs. Let's look at the parity generator next. So in the parity generator, we produce a logic 1 on the output P if there are odd number of logic 1 on the input. How to implement the even parity? So first we need to understand the odd parity circuit. So what it does is P equals to 1 if odd number of logic 1. Okay, odd number of logic 1. So for example, if we have 0, 1 and all these are 0, so we're going to expect, so here we have an odd number because we only have one logic 1. So it's an odd number of logic 1 on the input, therefore our output P is for sure going to be 1. So let's analyze this. So here is going to be 1, here is 0, 0, 0, 1, 0 is going to be 1, 0, and therefore this is 1 correct. Okay, so in the case that we have even number, so let's say for example we have even number, so I have a 1 here, so now we have an even number of ones. What's going to happen is, okay, this is still 1, 0, 0, here is going to be 1, here is going to be 1, 1, 1, here is going to be 0, so it's correct. Okay, so in the parity generator circuit, if you have an even number of ones, the output P is going to be 0. If you have an odd number of 1, the output P is going to be logic 1. So if you want to have an even parity circuit, you can simply connect an inverter here. Okay, then we are going to have logic 1 since this is 0. So 1, 1, 0. So we have a logic 1 on the output, and then we have an even parity circuit. So let's move on to our last topic on the logical and arithmetic shifters. Okay, so a shifter is basically, it takes in an n-bit number and it's trying to shift to the left or to the right. So for this example, we're going to see it's a left logical shift, and also we also have the right logical shift. So in the left logical shift, what we do is we are going to take the right part here, okay, and we are going to transfer into this part. So we can see here this 0 is transferred there, this 1 is transferred there, transfer, so we transfer each one from one place to the other place, and this one is now gone. Okay, this one is now gone, and then the 0 is going to shift in and put it inside the rightmost. Okay, so if you can imagine that we are actually taking the right side of the bits, put it on the leftmost, and insert a 0 on the side. Now let's look at the right shift. So in the right shifter, we are going to take this side, okay, and then we are going to store it. Okay, so this is the original. This is the original, this is the new. So we're going to take this. So for example, this one here is 1. Okay, 0, 0, 1, 1, 0, and 0. This one is going to be gone, and this one we're going to put a 0 inside there. Okay, so now it becomes a new logic number or new logic values. So this is called the right logical shift, where we fit in logic 0. What about arithmetic shift? So a left arithmetic shift and a right arithmetic shift. So in the left arithmetic shift, what we do is we are going to this is, in fact, this is exactly the same as left logical shift. Okay, so left arithmetic shift is in fact exactly the same as a left logical shift, whereby we are going to take the right side, 7 bits, and we are going to just transfer these values to here. Okay, and now this is gone. Okay, and we are going to take the 0 and put it inside our LSB, or for the new, this is the original, and this is new. So for the new bits, after shifting, new after shift, okay, here is a new after shift. We're going to get a new binary bits or a new value. Okay, what about the right arithmetic shift? This is different. So the MSB actually fits the MSB. So what we do is we are going to take the original. So a right shift. We're just going to take this one. Okay. So these values, the 7 bits, we are going to put it to the right. So basically we are shifting the original to the right. So you can see that. And now what do we put inside here? we are actually putting the MSB of the original bits. Okay, so the original bits MSB is actually 1, so we are going to put 1 inside there, and this one is gone. Okay, so that is a arithmetic shift and logical shift. So make sure you know the difference between the left logical, right logical, left arithmetic, and the right arithmetic. So let's look at some examples here. Let's perform 1 bit left logical shift. So shifting to the left means that we are going to take this. Okay, so we are going to shift to the left. So it's going to be 1 1 1. Sorry, 1 1 0. So we're going to take this 1 1 0. Okay, and we are going to put a 0 inside. Okay, so this is the answer. So basically, if you can imagine, we are discarding this. Okay, we are discarding that, and we are moving the 1 1 0 all to the left side by 1 bit. Okay, let's look at the next example here. If we have like this, we are going to remove this. Going to take this and shift it to the left, so it's going to be 0 1 1. And because it's a logical shift, we are inserting a 0 at the end here. Okay, so this is the correct answer after shift, okay, from the original. Okay, so let's perform a right arithmetic. Okay, so this is an example for the left logical. So we do a 2-bit right arithmetic. So we can also do a 2-bit shifter. So a 2-bit shifter, let's look at the first one here. So 1 0 0 1 0. We can have any bits that we want. So 1 0 0 1 0, if you do a right shift by 1, so means that we are going to take these ones, okay, and put it 0 0 1, okay, right on the right side. Okay, so 1 0 0 is now pushed to the right, and what is going to be fed in through? So it's an arithmetic shift, therefore it's going to be 1 1. It's going to be fed through. Okay, so this is the answer. And then what about the next one? So here is 0 1 1 1 0. We are going to do a 2-bit arithmetic, so we are going to take this one, okay, and from the left side we are going to transfer to the right. So 1 1 0. Okay, and here is going to take, since the MSB is 0, so we are going to put 0 0, and this is your final answer after you are shifting 2-bit to the right side. Okay, so let's look at the last examples here. So the purpose of the shifters is to perform a fast constant power of 2 multiply and divide. So for example here, if we are given 8-bit decimal number 12, so 12 8-bit, okay, so 12 is 1 1 0 0. So for an 8-bit we have 0 0 0 1 1 0 0. So this is our 12. And if you do a 1-bit left shift, so if you can imagine, if you do a left shift of this binary number, we are shifting it to the left, okay, meaning that we are going to take this part. Sorry, so left shifting. So left shifting is we are going to take this part, in fact. Okay, we are going to take this, we're going to discard this, okay, and bring it to the left. So what happened is you're going to get 0 0 0 1 1 0 0 0. So it's arithmetic. Okay, left shift. So that's the answer here. So 0 0 0 1 1 0 0 0. Okay, and the decimal number here is in fact 24. Okay, so you can calculate the 2 binary there. So here it's a 16 plus 8, so it's actually 24, and here is in fact a multiplied by 2, since a is 12 and our answer is 24. So basically a 1-bit left shift results in a multiplication by 2. Okay, what about a 2-bit left shift? So a 2-bit left shift, so we have the original number. A 2-bit left shift, we are going to take this number, okay, and we are going to get 0 0 1 1 0 0, and it's an arithmetic shift. 0, 0. So that's our answer. So after a 2-bit shift, that's the answer we're going to get, and it's going to be 0, 0, 1, 1, 0, 0, 0, 0, and here is actually 48. So here is actually A multiplied by 4. So essentially you can say that a 2-bit left shift, arithmetic or logical in this case, will result in the original binary multiplied by 4. Okay, which is from 12, now we have our new 48. Okay, 16 plus 32. Now, what about 1-bit right shift arithmetic? So if you do a right shift, let's remove this. So if you do a right shift, this is our original number, 12. Okay, and we do a right shift. So we are going to take a 1-bit right shift. Okay, so 0, 1, 1, 0, 0, 0, 0, 0. And so this is the final answer. 4, 0, 1, 1, 0. And this is simply a 6. So here is A divided by 2. So you can see 0, 1, 1, 0 is essentially a 6. And it's actually a 1-bit right shift results in a divide by 2. And what about a 2-bit right shift? So a 2-bit right shift, so this is our original number, 12. And the 2-bit right shift, we are going to take this and shift it, 1, 1, 0, 0, 3, 4. Okay, so just shifting the bits to the right, insert a 0 at the end, and we are going to get 1, 2, 3, 4, 0, 0, 1, 1, and this is actually 3, and here is actually A divided by 4. So you can see that 12 divided by 4 is in fact 3. So it's a fast way, basically, to perform constant power of 2 multiply and divide. Okay, so that's it for our lecture notes for this week, and we'll continue with the next topic next week.